Okay, so welcome back everyone, and today we're gonna solve this question that is construct tree from pre-order and post-order. There are some prerequisites and some previous understanding we must have, and we will see what are the new understanding, and then we can go on drawing the explanation of the problem and then the code live walkthrough for Java and C++ references. So this is the previous question which we have done in past, that is construct binary tree from in order and post order, and we'll see what's the difference between binary tree and full binary trees, and then we'll proceed on with the question. But before proceeding ahead, here are two things. So this is our DSA repository, which consists of 500 plus problems. And whenever I solve a problem, I push that particular snippet or code solution into this one. You can start and fork to get help with your interview prep. I can already see 95 and 27 folks, so do not left behind and do the same. And here's our YouTube channel, so code and record. So we just solve up to problem of the day and then code it and record it for you guys so that we can share it within the community, right? So yeah, a bunch of the playlist. That is nothing but DSA 180 top interview question, problem of the day, DSA A to Z topic wise. You can go onto this playlist and explore all the topics here. That is from trees to graph to recursion and everything. Now let's jump back to the question and let's get started. So let me just share my tab screen and we'll go on one by one. So we need to construct from pre and post, right? So this is the previous question which I was asking you to go through it. If you have time, please go through it before proceeding to this one. You will have a good and a firm understanding and to solve this one, right? So सबसे पहले हम देख लेते हैं कि what is the difference between binary tree and a full binary tree, right? And what are the combinations for the order of traversals we need to form such particular unique binary tree? Or if not, if it is not possible, then what are the possible combination for the not possible ones, right? So binary tree is nothing but it can have at most two children, right? Which means it can have zero. At most means it can have zero, one, or two. But full binary tree, it says that it is either zero or two, correct? तो हमारे पास जो कॉम्बिनेशन है यार देखो हमारे पास जो कॉम्बिनेशन है फॉर लेट्स से इन ऑर्डर हमें चाहिए ही चाहिए एंड इफ वी गेट प्री और पोस्ट देन वी कैन फॉर्म अ यूनिक बाइनरी ट्री राइट हम यूनिक बना सकते हैं बट अगर हमारे पास सिर्फ प्री और पोस्ट है देन वी कैन मेक अ यूनिक फुल बाइनरी ट्री राइट so let's understand this with one example or let's say with one skewed tree example. So let's say you have this particular trees 1 2 3 and 4, right? And then you have this 1 2 3 and 4. So these are some two skewed trees. And if I ask you what would be the pre-order, post-order for both of the trees would be, so pre-order का क्या मतलब होता है? Just to have it handy in memorization, I memorize it like this way. So we have, let's say, in, we have pre, we have post, right? So in means left and right remain same. So left in means in between, right? So in between the root would be there, and left and right order remains same, right? In the pre, root would be first, and in the post, root would be at the last, and left and right. Just keep on writing this. So this is the pattern. You can also have it to memorize the things. And what is the pre-order for this particular tree, right? I can say 1 2 3 and 4, and the post order for this one would be 4 3 2 and 1. And what would be the pre and post for this one? It would be 1 2 3 and 4, and 4 3 2 and 1, right? So you can see that pre and post are coming to be same, right? So इस case में we cannot make a unique, we cannot construct a general binary tree, right? So there's nothing but why can't we construct the general binary tree from pre and post, right? And here goes our example, right? अगर आपके पास अब यहाँ पे वही इन ऑर्डर हो जाता, आप इन दोनों का इन ऑर्डर निकालोगे तो वो एक डिफरेंट कॉम्बिनेशन हमें मिलेगा एंड देन वी कैन से दैट वी कैन कंस्ट्रक्ट अ यूनिक जनरल बाइनरी ट्री. So this would be 4 3 2 and 1, and in order for this one would be 1 2 3 and 4, right? And that is the reason I said if I have in order plus either of them, pre or post, then we can construct the general binary tree. And if not, if we have pre and post, then we need to go for the unique full binary, and that the question says as well in the description, right? Okay, let's move ahead. So what actual test cases we have? So I'll be taking the second one. So 1 2 4 5 3 6 and 7. And then we have 4 5 2 6 7 3, 1. Okay. So this is the pre and this is the post. And we know in pre, what's the order? So it is root, left and right. And in the post, we have left, right, and root, right? So I can clearly say that this first node is the root of our possible binary tree. And this one is again the root in the post order traversal, right? So I can make a tree. So our expected output is like this, 1, 2, 4, and 5. We need to draw some pattern जिसमें हमें पता चले कि हमें किस बाउंड्रीज में रिकर्जन लगाना है, right? तो 1 हमारा यहाँ पे है and we can clearly see that this would be our root node in the post or traversal, that is the last node. But अब क्योंकि हमें पता है कि ये एक full binary tree बनेगा and the definition says that either it has 0 or 2 children, right? तो अगर 1 के बाद if there would have been no nodes, then I would have said कि कोई children है ही नहीं, यही एक tree खत्म हो गया, right? But definition कहता है कि या तो 0 होगा या तो 2 nodes होगा. तो if there are multiple nodes after this root node, then it is guaranteed that this would be the left child of my this first node, root node, right? So I can say that this would be my left child, right? Now I will search for this 2 into my post order, right? And now I can say since this is a root node, right? Since this is a root node, then I can say that this is my basically this is not root node is 1, but the left child of 1, right? So the entire left subtree would be this for our root node 1, and this would be our RST for root node 1, right? So I can say that this would be in the left hand side of our root node 1, the values would be 4, 5, and 2, and in the right hand side, the values would be 6, 7, and 3. I don't know the exact order now, but this is for sure. And you can clearly see from the expected output as well, right? So that is one observation here, right? We need to do the same for this combination now so that we can reach on to the last recursion track and then we recur back to get the node back, right? I hope you got the intuition now. Okay, so similarly for this two now, for this two, since there are multiple nodes beyond this right hand side of this two, then I can say that the left node of this two would be 4, and then I will search this 4 here in our post or traversal, and there are no nodes on the left hand side of this one, right? So I can clearly say that this is the LST of our root node 2, right? And this is the RST. This is the RST of our root node 2, which is nothing but 5. Similarly, the tree would be forming here as 3. This would be 3, and this would be 6 and 7, right? Now, what would be the pseudo code for this one or the exact code? तो इसका ड्राई रन दिखाने के लिए यार मैं यहाँ पे अपना एक्चुअल कोड लेके आऊंगा, right? And then we will do a dry run of that because that will make more sense to us. Hmm. So let's do a dry run now for this code. So again, यहाँ पे कंस्ट्रक्ट ट्री का हमारे पास एक फंक्शन होगा एंड देन वी हैव अ प्री इंडेक्स एट दिस पॉइंटर, राइट? एंड वी हैव अ पोस्ट स्टार्ट एंड पोस्ट एंड फॉर दिस पर्टिकुलर पोस्ट array traversal in which we will be traversing to find our left child of our current root node, right? And then based on that, we're going to decide what would be the LST and RST for our current root node. Okay. So in the construct from pre-post, we have 4 parameters, that is pre-array, the post array, the pre-start, and the post end, right? And these are the cases. The base case where post start is greater than post end, definitely there if there are no elements to traverse through, then in that case we'll return null. And okay, let's start the diagram and then we will see. So this is the index 0, 1, 2, 3, 4, 5, and 6, right? And we're gonna be starting from 0, comma 6, right? And the first node we will be making is of and in the pre-index. At this point, the pre-index would be equals to 0, right? And we'll be making the first node here. So 1, 1, this is the one, right? And then we increment it. Once we made the node, we increment at the same time. So that means pre-index becomes 1 now, right? So let me write like this. Is 0, it becomes 1. ऐसा क्यों कर रहे हैं यार? देखो हमने इंट्यूशन में क्या देखा था कि अगर हमारे पास रूट नोड है, then we go on to the next node, form search its left child of our current root node, and then we search on in the post array to decide the LST and the RST for our current root node. ये decide किया था हमने, तो वही करेंगे, वही कर रहे हैं यहाँ पे. So we are making the root node 1 here, and we'll be going to the pre-index equals to 1, which is this one. We're gonna search it in the post array. So here the searching is happening, right? And then we are marking this index as I. Now I know this is my LST and this is my RST. So that is the reason in the left call we have said a pre-post and then post start, that is post start and comma I, right? Similarly, the LST will have I plus one till post end minus one, because this last node is again the current root node from our post order traversal, right? So post end minus one, and then we return the root. So let us complete the diagram now. So here the values would be passed as here we made a node one and then the index we found was two, right? This index, because this value 2 was present at this index 2, right? Now, we pass the recursion call for 0, comma 2, right? And then what is the next step of the node we played? So we made the, यहाँ पे, we actually had pre-index is equals to 2, right? And we made a new node for pre-index equals to 1, that is 2. And then we pass on, we search for this 4. We search for this 4. Let me erase the pointers now, and we search for this 4 and we get here, right? And we can see there is no values present on the left of the 4. That means we have our 2 as this, and then we made a call for 0, comma 0 in the left hand side, right? And here our pre-index would be equals to 2, correct? And then here we made a node for 4, and now you can clearly see here that here is our one base case, that if post start is equals to post end, right? Then in that case we will return this root node. So हम return किया हमने, and then we make a linkage between 2 to 4, right? And then we go on to our next recursive call, that is to the right hand side, right? And we called, or let me write like this, and we called for the indexes, which is nothing but 1, comma 1, right? Right के लिए हम क्या कॉल कर रहे थे? I plus 1 and post end minus 1. This is our I, so I plus 1 is 1. Post end, which is 2, 2 minus 1, which will give you 1, right? Now again, the post end and the post start matches, right? So at this case, at this call, our post index, here it was 1, 2. Uh, at this point, our post index would be 3, right? Because we are incrementing in each recursive call. So this is our fourth recursive call, right? So starting from index 0, this would be 3. And at 3, the node is 5. So we'll be making a node 5. And since post end and post end matches, so we'll be recurring back and we'll be making a linkage to 2 to 5. So currently, our tree is looking like this. So this is 1, this is 2, this is 4, and this is 5. So itna tree हमारा बन चुका है, right? Similarly, the calls would be going from here, and this will call for 3, comma 5. This will call for 3, comma 5. If you remember, here was our first I for the first recursive call, and this we passed, right? So this is 3 and this is 5. So again, here the pre-index would be, this is the fourth recursive call, right? So 4. Similarly, for 3, comma 5, uh, here before calling for pre-index plus plus, a new node would be made on this index 3, which is nothing but on this index 4, basically, which is nothing but node 3. And similarly, the next recursive call, which we'll be having for, like, this is the fourth index 3, right? And the next is 6. So we search for here is 6, and we get that index as 4, comma 4, right? This one. Uh, just a second. So here, the node 4 was made, right? And the next node for this particular pre-index was 4, and the node 3 was made, right? And the next node after 3 was 6, and we searched for 6 here, and then we got I as this one, index 3, right? And our post start was 3, so we will pass 3 and the index I. In the left call, we were passing post start, comma I, right? So that would be it. And then since the post start and post end is again the same, so at index 3, what is the value? At index 3, the value is 6. So a node 6 would be returned from here. So as of now, the calls 3 and the 6 linkage is made. And similarly, the last call which we'll be having here is so this index post index 4 here it will become 5, and this here in the uh, pre-index 4, 5, and 6 is the last recursive call, and here the node is basically 7, and the recursive call would be called for 4 comma 4. So here it is 7, right? So we search for 7 in our post index array. That will our I would be here, and we're gonna pass I plus 1. So basically I is pointing at 4, so I is pointing at 4, right? So we wanna be we already made that recursive call, right? So definitely in the right hand side call, the parameters were I plus 1 and post and minus 1. So this is I. So 3 plus 1, 4, and 5 minus 1 will be 4. Correct. And that's it. And we will return the node 7 from here, and then this linkage would be complete. तो ये रिकर्जन थोड़ा भारी था यार रिकर्जन ट्री बनाते हुए थोड़ा सा इधर उधर हुआ है, बट आई होप यू वर एबल टू अंडरस्टैंड, राइट? इफ नॉट देन आपने पेन पेपर के साथ मेरे साथ नहीं किया होगा, एनी सूडो कोड साथ साथ नहीं देखते गए होगे आप, तो एक बार वापस से देख लो एंड यू विल बी एबल टू गो थ्रू इट, राइट? So here is our exact code now. So what is the time and space for this one? Clearly I can see that for each and every node we are searching in an array. So O of n square and O of n as space, right? As the recursive stack space, you can say. Now, what is this thing? Mm, what is the further optimization that we can make in this code? Here, the space would be n because in the worst case, a skew tree would be given to us, and the recursion space would be taking recursive stack space would be stacking all the nodes for the function call, and then O of n would be our worst case, right? Let us compile this code, and then we can move ahead with the optimized one. The only optimization which I can see is that here we are using of a linear search here to provide a search into an array, right? And if we are able to store the indexes, right? If you're able to store the indexes corresponding to its value, then we can basically get that value in O of 1. And the best way to actually to do this would be hash map, right? So we're going to be doing some pre-processing before the recursive call. We're going to be making a global hash map so that it can be accessible across all function. And then we will be calling dot get function to do this task. So let me do that optimization, and then we can uh, resume back. Yes, so here are the changes. We have made a global hash map so that it can be accessible across all the functions. And we are storing all the post uh, traversal values in a post map. And then instead of doing a linear search, we are just getting it from our map, right? And that gives us O of 1. So as this get function call. But overall, the diversity changes from n squared to n, and the space remains same. Now let me give you the C++ reference. So here is the C++ reference for the C++ users. You can take help from this code, right? It's doing the same. And again, a few last thing, if you're new to this channel, please like, share, and subscribe. And because our target is to hit 10K by the end of this year, so do share your support. And that's again a DSA repository. You can start and fork. And that's it for this one. Let's meet again in the next video.